Thank you. As you said, I'm Kirstie Queener, happy to be here and happy to be talking about conformal electrodes. So today's presentation, I will be introducing conformal electrodes just in case no one is aware. I'm sure most of you are. And then I will go into the fabrication of our electrodes, the electrical characterization, physiological recordings that we performed, and then as well as future work. So in general, conformal electrodes are thin and soft, which enables them to curve to many skin areas, a wide range, and this allows for a wide range of recordings of the body. The close contact of these conformal electrodes brings the potential to eliminate the use of gel for electrodes in the readings, and reduces the overall thickness of the electrodes on the skin. This in turn leads to improved compatibility with hairy skin or wet skin adhesion. And these interfacial advantages allow for the reduction of motion artifact when compared to standard off-the-shelf standard electrodes. But while these conformal electrodes show improvement compared to the standard electrodes, we still need to do more work in improving the fabrication process and the reliability of these electrodes. With that, we are investigating the micropatterning of conformal electrodes. So the micropatterning allows for the introduction of conductive polymers such as P.PSS, which just reduces further the interfacial impedance and motion artifacts, particularly in biocompatible skin-worn applications. So we wanted to know by micropatterning these electrodes, what that had an effect on the insulation layer, how it impacted the electrical characterization and the ultimate effect of the electropolymerization of E.dot to P.PSS. So in our study, we had 3 different design variants, the first of which was a control. So this is just a blank gold electrode, no insulation layer. I'll call it variant 1. We had variant 2, which is a spiral pattern of 60 micron diameter vias down to the gold from the parylene layer. And then variant 3 is 30 micron vias, also in a spiral pattern similar to variant 2. Went too far. So now I'm going to go over the fabrication process that we used to make these conformal electrodes. So we first started with our carrier wafer, which was PDMS coated soda lime wafers, and we added 38 micron PET sheets. We laminated them onto the PDMS. We then used E-beam physical vapor deposition to deposit chromium gold metallization layer on top. And then we used AZ1518 photoresist to create an electroplating mask. And then gold was electroplated using a TSG 250 solution, which resulted in trace thicknesses of 200 to 250 nanometers. We used this photoresist again to define the electrode shape. And then we use parylene C coating to then dry etch the vias down to the gold. So the bottom. The bottom image is the gold electrode before P.dot was electropolymerized onto the surface, and you can maybe see the spiral of vias. And then the top image is following the P.dot electropolymerization, and so you can see the spiral of the P.dot within the vias. So this is the first variant. The left side is bare gold before P.dot was applied. The right side is bare gold after P.dot was applied. So essentially just P dot, not very interesting to look at because it's just gold. This second set is a little bit more interesting to look at. So the first side, you can see the vias and how they were etched. And then in the second image, you can see closer that the P dot sits just below the surface of the parylene all the way down to the gold. And then this is the third image, third variant. And in the second image, it's a little more difficult to see the exact location of the P dot because of poor forming of the vias on this particular electrode. But you can see the vias in their formation on the right side here. We then performed electrical characterization on both the electrodes prior to electropolymerization and post adding of the P dot. So in this first graph, you can see it was higher impedance. We use electrical impedance spectroscopy from 1 Hertz to 100 kilohertz in galvanostatic mode on a potentiostat galvanostat. And the takeaway from these two graphs is that the addition of P dot reduces the overall impedance in each electrode variant across the board, especially at low frequencies. So like I said, the reduction of impedance was very apparent at low frequencies. We saw significant reduction in all 3 variants, control, 60 micron, 30 micron, and the 60 micron vias, even prior to the P dot deposition, were comparable to standard off-the-shelf electrodes. All 3 electrode variants post P dot deposition are all lower impedance than standard electrodes. At higher frequencies, however, it's a little bit of a different story. 2 out of 3 were not significant, but the middle variant was significantly increased after the P dot deposition. So that is not what I anticipated to happen. So we want to do some further digging into why this might have occurred. And then following the electrical characterization, we then moved on to looking at physiological recordings. We demonstrated the integration of these electrodes and the performance of the micropatterned electrodes in a wearable device. First of which was a heart rate measurement. So we had simultaneous recording where we had 3 standard electrodes, the 3M red dots, and then we had 3 of our micropatterned conformal electrodes above. And then for the breathing test that we did, it was, oh, sorry, put the wrong button. 4 of our conformal patterned electrodes, and we used simultaneous 4-wire bioimpedance and triaxial acceleration to record while the patient or person performing the test performed fast, shallow breathing. So these are the results of the heart rate measurements. We were able to detect heart rate from the potential measurements, and this confirmed that we saw similar signal quality and synchronization of the heart rate heartbeats for both the conformal electrodes and the standard electrodes. And you didn't really see a difference between the variants in each of these cases. So that's why we want to test these electrodes for longer periods of time. So it's only 20 minutes. So we want to test them over hours and days to see if over time the accuracy of one variant over the other changes. Then we have the bioimpedance results. So we were able to detect the breathing rate from bioimpedance and inertial measurements, and we saw an insignificant difference from these extracted values. So again, we want to test over longer periods of time to see if the variants maybe change in accuracy. In terms of future work, we have a lot of work to do on the fabrication and design, since that was the one of the main goals. We want to optimize the design to remove the need for isotonic gel. I think I failed to mention this. On the heart rate portion, we did have to use gel to get the conformal electrodes to stick to the body. So we want to further investigate the design and fabrication process to remove that need. And then further explore the impact of the design, maybe by recording for longer, like I said, for both heart rate and the breathing rates, and then further characterize the performance during dry operation. And then furthermore, we want to explore the effectiveness potentially in other applications, and then conduct more biocompatibility testing. So with that, I would love to thank all of my wonderful colleagues, especially the authors for this paper. Without them, this work would not be done. And if you have any further questions, here is my email address and my lab's website. Happy Halloween. Thank you.